Good afternoon. This is Math 2414. It's April the 30th. This is our last lecture of the semester. A couple of announcements to make at the beginning here. First of all, weekly homework is due by the end of the day today. I know that I had told you that it was due yesterday, but I decided to give you an extra day to do that. The assignment for that is in the notes from the end of the April 25th lecture, and it has to do with Taylor series. And so if you have not done that, you still have time. I'm posting this video at 1:30 on Monday afternoon rather than 7 o'clock like I usually do. And so you still definitely have time to finish that up and turn it in by the end of the day today. That'll give you 10 daily grades for the semester, 10 weekly homework assignments. I will drop one of those. And then the rest will be averaged and be your homework grade for the semester. That counts 20% of your final grade. All right, some notes about the final exam. The window for the final exam runs from May 3rd through May the 7th. That's this Thursday through next Monday. Note that the window ends on Monday, May the 7th. A review with comments on that review are posted on the Google site for the class. A one-page review summary, so kind of like a shortened version of the review, I sent to you by Remind yesterday, and it's also included at the end of these notes from today's class. I will have an online help session, and I have sent this out by Remind also. I have an online help session scheduled for my calculus class Wednesday, May the 2nd from 8 to 9:30. So show up for my in my WebEx office. I'll be happy to help you out on Wednesday, May the 2nd, 8 to 9:30 p.m. You can also make other times by appointment, but I will be online specifically for my calculus students from 8 to 9:30 on Wednesday. Also, let me remind you, and I've mentioned this through Remind and in the notes, that you can use a 5-inch by 8-inch, 5-inch by 8-inch note card or index card, right? Sometimes you'll see that referred to as an index card also. You can use that for notes and bring that in with you to take the final exam. So you can put anything on there you want to write down on that index card. That index card must be turned in when you are done taking your final exam. You will be asked to turn it in by the testing center. So please make sure that you turn that note card in. All right, so please let me know if you have any questions these last few days as we're heading into the final exam. I'll be happy to try to help you out. Also, don't forget that the final exam does replace the lowest exam grade. So if you have a low exam grade out there, you can still get that replaced by the final exam. All right, so today we really only have a short topic to cover to kind of finish up the class. And this is on using known Taylor series to create other series. And so that's what we want to talk about today. So first of all, let's kind of remind ourselves here that let me insert an empty page here real quick in the right spot. Don't forget that a Taylor series centered at C. So a Taylor series for a function f of x centered at x equals c is a series that looks like this. The sum as n goes from 0 to infinity of the nth derivative evaluated at c divided by n factorial times x minus c raised to the nth power. Don't forget that I referred to these coefficients right here. These are the Taylor coefficients for a Taylor series. It's always the nth derivative of a function, of the function you're talking about, evaluated at c divided by n factorial. We spent a lot of time talking about this definition for a Taylor series last time. Also, don't forget that a Taylor series that's centered at 0 is referred to as a Maclaurin series. I don't usually use that distinction. I just refer to them all as Taylor series. But if you're reading through a textbook or looking at other videos, possibly they may talk about a Maclaurin series. The Maclaurin series is simply a Taylor series centered at 0. Okay, so I wanted to make sure that we had that written down again. It kind of reminded you of that. So if you write out the terms here, this is the 0 derivative, which is the function itself, evaluated at c divided by 0 factorial times x minus c to the 0, plus the first derivative, f prime, evaluated at c divided by 1 factorial times x minus c to the first, plus the second derivative, evaluated at c divided by 2 factorial times x minus c to the second, and so on. Don't forget also that 0 factorial is defined to be equal to 1. And the zero derivative is just the function itself. Okay, so we're talking about series that are in this form, and it is just a version of a power series. So we have these known series, and we actually derived a couple of these in class last week. We derived the series form for cosine x, for e to the x. I believe we also did one for 1 over 1 minus x, possibly, things like that. So you have these known Taylor series, with their intervals of convergence. Don't forget that the cosine function and e to the x are nice because those converge for all x, which is good. For example, the one for 1 over 1 plus x, this one only converges from x from -1 to 1. Remember, it's either going to converge for all x, or it's going to converge in a symmetric interval around the value you're expanding the series around. So like the series, notice that I've got for 1 over 1 plus x is centered at x equals 0, so that has to be a symmetric interval around 0. In this case, it's from -1 to 1. And so on. One thing you can do within these intervals of convergence for these functions is you can go ahead and derive other series from these. So for example, cosine of 3x, all you're doing is using substitution here. You're simply taking the original series, and every place you see an n, you're just replacing it with every place you see an x, you're simply replacing it with 3x. So in this case, this would be 3x to the 2n power divided by 2n factorial. Right, that would be the series for cosine of 3x. Now, you usually try, if you can, to somehow simplify those to make them look a little bit better than what I've got written right there. So, for example, that 3n, it's possible, that 3x raised to the 2n, it's possible that you might see that written as 3 to the 2n times x to the 2n. In fact, it's likely that you're going to see it written that way, divided by 2n factorial like that. And so, in fact, that 3 to the 2n, that could be written as 9 to the n, and so you might actually see it written that way. That would be a common thing to see. So you'd have -1 to the n. The -1 to the n as a factor is usually left kind of separate because that's the factor that kind of makes the series alternate. And then you'd have, 9 to the n over 2n factorial, right? And that would be the coefficient. And then this would be times x to the 2n, like that. And that would be a more common way to see it. Now, you'll also see, you can just abbreviate it or substitute into the sigma notation. Don't forget what the, let me move these functions down. Let me give myself a little bit more room right here. Don't forget that you could actually write out the form for the cosine, the actual Taylor series for cosine x. You know that cosine x is going to be 1 minus 1/2 x squared plus, so you have, that's, remember, that's 2 factorial, and then the this would be 1 over 24 x to the 4th, and then minus 1 over 6 factorial times x to the 6th, and so on. Okay, and so cosine of 3x, sometimes you'll see it done this way, where the 3x is just substituted in each x value right here. So we're simply using substitution, and within the intervals of convergence, this is going to be okay to do this kind of thing, right? And so you'd have that written out like that, and so then you could finish that up and write this as 1 minus, and this would be 9/2 x squared plus 3 to the 4th power would be 81, so this would be 81 over 24 x to the 4th. 3 to the 6th power, that's 3 squared times 3 squared times 3 squared. It's 9 times 9 times 9, so that's 729. All right, so you have 729 over 6 factorial, which is 120 times x to the 6th, and so on. So that's another way that you'll see a series for something like cosine of 3x derived. Okay, so let's see. Let's draw a line here. Let me move this down just a little tiny bit more. So if I draw a line, so we can kind of separate these out. 1 over 1 plus x squared, we're simply using the series for 1 over 1 plus x that I have written up at the top. But in place of the x, I would simply write x squared. So this would be x squared to the n. Now this one's really very simple to write out, right? You'd simply write this as the sum as n goes from 0 to infinity of -1 to the n times x to the 2n, because you multiply the exponents. And so that would be the version or the series, the Taylor series representation for 1 over 1 plus x squared. All right, and then we would have e to the -x squared. Move that one up a little bit. So we see above the series representation, the Taylor series expansion for e to the x. So we would substitute -x squared. And we have x to the n. So in place of x, we would substitute negative x squared, and that would be to the n over n factorial. And so notice in this case, this actually changes this series to an alternating series, because that -x squared is really -1 times x squared to the n over n factorial. And so that gives us -1 to the n times x to the 2n over n factorial. Okay, so the series form, the Taylor series for e to the -x squared expanded out, actually written out, would be when n is 0, then that would just be 1 still, right? But when n is 1, now you have that this is going to be negative, and this is going to be x squared over n factorial, which is 1 factorial, so it'd just be x squared. The next term, when n is 2, you would now, that would be a positive term, and you'd have x to the 4th over 2, and then minus, and the next one would be x to the 6th over 3 factorial, which would be 6, right, and so on. Next term would be when n is 4, and so it'd be positive, it'd be x to the 8th, and this would be over 4 factorial, which is 24 right? And those would be the first few terms of e to the negative x squared, like that. Okay, so using substitution, this is a possibility for the final exam, where I would give you one of the 4 series at the top of the screen here, or I give you a series that's related to one of those, and then you would simply use substitution to write out the series. So it should be pretty straightforward to be able to do the work through a problem like that. Those 4 series at the top, cosine x, e to the x, 1 over 1 plus x, and arctan x, I would strongly advise you write those on your note card, because those would be the known series that I would refer to on the final exam. So pay attention to that, and make sure that you have those written in your note card that you take in for your final exam. Okay, so now I've got those series written down again, so now let's do this in a different way. Let's use calculus. What happens is that within the interval of convergence, now the edges of the interval of convergence could change here as far as whether they're included or not. Remember, sometimes those endpoints are included, sometimes they're not included in the interval of convergence. Outside of those endpoints, the interval of convergence doesn't change here, and we can actually use differentiation or integration term by term to generate a series. So for example, first example there says use the series for arctan x to find the series for 1 over 1 plus x squared. See, we know that the derivative of arctan x, the inverse tangent of x, is 1 over 1 plus x squared. So then we ought to be able to differentiate that series at the top, and that I've got written down term by term, and then we could create the series for 1 over 1 plus x squared. So let's see if we can do that. So, and notice you can actually do this in the sigma notation if you so chose to do that. So this is the sum as n goes from 0 to infinity of -1 to the n. That's just a constant. It's either a positive 1 or a negative 1. So when you differentiate, if you think about that, that won't change. What changes is this variable expression. So here's our function, x to the 2n plus 1 over 2n plus 1. And so if we find f prime, if we differentiate that term by term, notice we get the sum as n goes from 0 to infinity of -1 to the n. And all you're doing is using the power rule. So this is going to be 2n plus 1 times x to the 2n plus 1 minus 1. Right? That's simply the power rule, because you just have a power of x. And the 2n plus 1 in the denominator doesn't change, because it's a constant. So notice the 2n plus 1s divide out, and you get the sum as n goes from 0 to infinity of -1 to the n times x to the 2n. Right? The 2n plus 1s go ahead and cancel out. And that should be equal to 1 over 1 plus x squared, because that's the derivative of the arctangent, right? And that's just what we did. Now, if you flip the screen, notice that that's exactly what we got in this second to last problem here. We found 1 over 1 plus x squared by substitution there. Here we're finding the exact same series using differentiation. So works out really well. Now with integration, let me move this up a little bit here so we have a little bit of room. You do have to be a little bit careful because of this arbitrary constant stuff, but let's see, it says use the series for 1 over 1 plus x to find the series for the natural log of 1 plus x. See, we know that if you integrate 1 over 1 plus x dx, that you get the natural log of the absolute value of 1 plus x, right, plus a constant like that. So we ought to be able to then use the series for 1 over 1 plus x to derive the series for the natural log of 1 plus x by doing term-by-term integration. Okay, so here is my series. Let's see what we've got here. We've got 1 over 1 plus x, we know, is our function, and that would be the series. The sum as n goes from 0 to infinity of negative 1 to the n times x to the n, like that. So if I integrate that, term by term, just integrating that term by term here, we should get the sum as n goes from 0 to infinity of negative 1 to the n, and then this should be x to the n plus 1 over n plus 1. Like that, because you're integrating term by term. This is just a power rule problem. You add 1 to the exponent, and you put the reciprocal in front. Now this would be plus some arbitrary constant right here. Now, and we are hoping that this should be equal to, or not hoping, that we know that this is going to be equal to the natural log of 1 plus x, like this. Now what you can do to find the arbitrary constant here is you can go ahead and substitute x equals 0, and if you substitute x equals 0 in, right, all the terms in the series all go to 0 because of the x that you've got in there. And so what you end up with is 0 plus c equals the natural log of 1. And so you get that in natural log of 1 we know is 0. So you end up with c equals 0 here in this case. Now that won't always happen, that you'll get the constant to be 0, but in this case you do. And so that would be the constant, or the series representation for the natural log of 1 plus x there. Right, now you could have also certainly have done this term by term as well. If you had chosen to do that, that would have been fine. And you could have derived the series that way and looked at the series actually integrating term by term like that. All right, so now so that's how you could use integration to find a Taylor series representation for a function from a known Taylor series. So how can you use all this stuff? Well, an important application in probability theory involves a function that's sort of in the form e to the negative x squared. It's not exactly in that form, but it's related to e to the negative x squared. The problem with e to the negative x squared, and you end up with a definite integral that involves e to the negative x squared. The problem with e to the negative x squared is that there is no closed form antiderivative for this function. There's no nice, I put nice in quotes here, closed form version of this antiderivative. So in other words, the function doesn't really have an antiderivative that we can write down as a function like this. So instead, what we do is we simply use the version of the Taylor series version for e to the negative x squared. So we just wrote this down on the last page. Remember, we just substitute negative x squared in place of n here over n factorial. And so we get this series to be the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n over n factorial. So that series, term by term, and I wrote this down earlier, is going to be 1 minus, when n is 1, this is going to be x squared over 1, plus, when n is 2, this is going to be x to the 4th over 2, and then minus, when n is 3, this is going to be x to the 6th over 3 factorial, which is 6, and so on. Let's do one more term there. Plus, when n is 4, you're going to have, it's going to be a positive term, and you're going to have x to the 8th over 4 factorial, which would be 24, and so on. So to integrate negative 1, the integral of e to the negative x squared from negative 1 to 1, what you do is you take the Taylor series expansion and you integrate as many terms as you feel you need to achieve the desired accuracy that you need. The more terms you use, obviously, the closer you're going to get. So you can approximate this integral by looking at this problem. And this would be the integral from negative 1 to 1 of 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6, for example. Right, you could actually find the antiderivative for that function and evaluate. So you'd have, what would you have here? You'd have x minus 1/3 x cubed plus, and this would be, let's see, x to the 5th, and this would be 1/10 x to the 5th. Let me try to write all these terms kind of similar, right? Because you have x to the 5th, and then you have a 1/5 in front. And then the x to the 6th term becomes x to the 7th. And then you have 1 over 7 in front, so this would be 1 over 42. And this would be evaluated from negative 1 to 1. Right, and this would be an approximation for the integral above. So this approximates the integral. All right, so you could actually enter that function on a calculator, for example, and find the decimal value for that, and you'd get an approximation for that integral. So, if you'll bear with, so to integrate e to the negative x squared from negative 1 to 1, we use various approximations, Taylor series approximations for e to the negative x squared. So I've got e to the negative x squared written in the box off to the right on this screen. We have the first 5 terms written out, 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6 plus x to the 8th over 24. So you'd simply take the e to the negative x squared and replace it with the number of terms that you feel like you need to achieve the desired accuracy you need. So notice I've taken e to the negative x squared, here's our function right here, and I've replaced it with the first few terms of its Taylor series expansion. And then I integrated, and so here's the integral I've got in the red box here. Here's the antiderivative. It's a polynomial, so an easy antiderivative to write down. I evaluate that from negative 1 to 1, and I get this approximation right here, 1.4857. And so we see that the approximate value for the integral from e to the negative x squared of e to the negative x squared from negative 1 to 1 is about 1.4857. If I want better accuracy, I simply use more terms. So notice that's what I've done below, is I've used more terms. I just added an extra term on. These are alternating series, so remember the bound on the error is always given by the next term of the series. So you could always also figure out what the bound is on the error for these by simply looking at the next term in the sums that we're writing down. So there's my new approximation for e to the negative x squared. I go ahead and find the antiderivative for that one using term-by-term integration, just a polynomial right here. I evaluate that one from negative 1 to 1, and I get approximately 1.4949. So that would be presumably a better approximation than the first one. By the way, if I actually, on my calculator, this is just a TI-83 I'm using, if I simply graph e to the negative x squared and go ahead and get a decimal value for the integral, for that. So I'm going to graph that function. And then go ahead and find the integral from -1 to 1. From a calculator, I get directly e to the -x squared dx is approximately equal to 1.4936 to 4 decimal places, 483 from there on out. So notice we're getting pretty close. What happens is, because this is an alternating series, as you add more terms on, one term will be a little bit too small, the next term will be a little bit too big, the next term will be a little bit too small again, and it'll flip-flop back and forth around the actual value. So the actual value is approximately what I have right here. The calculator is pretty accurate in its algorithms that it uses there. So that's a pretty good accuracy on the integral there. And we're using these Taylor series expansions. We're just using the first 4 or 5 terms here. And notice we're getting pretty close to that actual value. So this is one way that Taylor series expansions are used, is they are used to replace functions where the integral or the derivative would either be impossible or at least very complicated to deal with. And replacing these functions with polynomials, where we can work with polynomials a lot more efficiently, probably. So that's a use for Taylor series expansions for functions. All right, so that's going to be my discussion for the day on Taylor series. We've gone through and we found different ways of creating new Taylor series expansions from known Taylor series expansions, and then I've shown you an example of how you might actually use a Taylor series expansion in a problem. All right, so let's go back and talk about the final exam here again for a minute. Now, this is the one-page review that I sent out yesterday using Remind. So I've got the 3 exams written down, and what I've done is I've omitted problems. These are problems not from the reviews, but from the exams themselves. These are all problems from the exam, and those are problems, whatever that particular problem covers, that I'm not going to be covering on the final exam. Everything else on those 3 exams is fair game for the final exam, basically. So notice on the exam 3, some of the, with the omitted problems, notice that I'm actually omitting the integral test and telescoping series from the final altogether. And as you go through, you'll see various different topics that are omitted. So for example, in exam 1, work problems, a long time ago that we covered those, but those are going to be omitted from the final exam. And then stuff since exam 3, 3 things. And so basically 3 problems that you will see on the final that are things that we have covered since exam 3. First is using a ratio test to find the interval of convergence and the radius of convergence for a power series. So I would point you to the lectures from April the 16th and April the 25th. For those, we worked out numerous problems for doing that process, going through that process. And so you see lots of good examples worked out in the notes for using the ratio test. Number 2, I'll give you a function and ask you to use the definition of a Taylor series. So when I say the definition, I'm talking about the series representation that with the Taylor coefficients that we've talked about, right? Where you've got the nth derivative of a function evaluated at c divided by n factorial times x minus c to the n. That definition, and I'm going to ask you to use that definition to create a Taylor series expansion for a function. I'll give you a function, ask you to create the Taylor series expansion for that function. Again, we worked through on the April the 25th lecture at least 3, maybe 4 problems like that, where we actually went through and created the Taylor series expansion. I will not ask you on the final exam to actually derive the interval of convergence for that series. I'll just ask you to derive the series itself. So that'll be another problem. And then the third problem that I'll ask you, like what we just did in lecture today, using substitution, differentiation, or integration to create a Taylor series from a known Taylor series. And again, the known Taylor series is what we've just talked about. And I would also say the April the 30th lecture here, that in other words, today's lecture. So you can go in and see how I did that. So I'll give you one problem, ask you to use either substitution, differentiation, or integration, term by term, to create a Taylor series expansion for a function given a known Taylor series. And you've got those 4 known Taylor series are the ones that I'm going to use for that particular problem right there. So that's why you're writing those down, because I'm going to base problem 3 in this group of problems off of one of those known Taylor series. So make sure that you've got those written down on your note card. And remember, the note card is a 5-inch by an 8-inch index card. You can put any notes that you want on it. I don't care what you write on that note card. You can bring it in with you to the final exam, but that must be turned in with your final exam. You please turn that in with your final exam at the end of the lecture. All right, so remember that I do have a help session Wednesday. A help session, an online help session in my WebEx office. Online help session, WebEx office. And that will be Wednesday, May the 2nd, from 8 to 9:30 p.m. So do not hesitate to stop by my WebEx office. Remember, the link for that is on my Google site. And you can ask me questions about old exams, whatever you feel like you need to going into the final exam. All right, so work hard going into this final exam. Let me know how I can help. I'll be happy to help you out. Good luck this last week, and good luck with final exams in general. Thank you.